So this is the second part of my chump build. In the last part, I talked about the program counter and the clock that we built and how it counts up. The first thing that I'm going to talk about is the program EEPROM. So this will take our program the code that we did in the first part, and it will convert it to 8 LEDs to show the zeros and ones that we have, and it will also send the signal to the control EEPROM and the multiplexer. These will be used for later. The control EEPROM takes the control codes that we will have programmed on, so the actual command for add or load or subtract, any of those commands will be loaded onto the control EEPROM, the same way it's loaded onto the program through the TL866 or Universal Programmer. These outputs at the top here, the highest 4 outputs, are sent down to be used in the ALU, and the other lowest 4 outputs will be sent along the two highest of the low 4s will be used in the mode and CN carry output pins on the ALU, and the lowest 4, the second lowest one, will go to the accumulator, and the lowest will go to the RAM chip. The next part I'm going to talk about is the address. This is a 6 input, 6 output flip-flop. We will be using 5 of them. 4 come from the multiplexer into the address and go out to the RAM, and the last one comes in from the control EEPROM. That lowest bit goes into the RAM, but first it goes into the address then it goes into the read-write pin on the RAM. The next part that I'm going to talk about is the multiplexer. So this will take the inputs of the lowest 4, which will be the constant, we'll call, in the program EEPROM, and the inputs from the RAM chip that I will talk about, and it puts one output that goes to the program counter, the address, and the ALU. The next part is the accumulator. So this part is basically the same as the address, except it is an octal flip-flop, and it has a... Next, I'm going to talk about the ALU. So this is the biggest chip. It will be able to perform all 16 logic operations, stuff like AND, OR, NOT, NAND, all those kind of operations. So it takes inputs from the accumulator, the accumulator output, or the outputs from the accumulator go into the ALU, and they also go into the inverter for RAM. And then the other inputs, so it has A inputs and B inputs. The B inputs come from here, which is from the multiplexer, and it goes into the program counter, address, and ALU. So that's the second input. Then there are select pins on the ALU. That will come from the top 4 outputs on our control EEPROM. That goes down into the ALU as select pins. Now there's a few special pins. The carry output pin comes from the control EEPROM as well, and the mode pin also comes. And then there's a final pin here called the A equals B pin, and we will put that to high with a 2.2 kilo ohm resistor, and this will go into a NAND gate. So the reason this NAND gate is here is to trigger the load pin on the program counter to use a go-to command so we can go to a certain line of code. So to trigger this, we need a low on the end of this NAND gate. So to get a low on a NAND gate, we need 2 high inputs. So we have 1 high input coming from the A equals B pin. The second high input comes from the 2 outputs on the program EEPROM that are the highest ones, IO7 and IO6. Those will go into an AND gate, and when they are both positive or both high, it will produce a high that goes into NAND gate. The high and the high make a low, which sets the program counter's load pin to low, allowing us to send a different program line through. So if I go ahead and plug the chump in, we can see a bunch of LEDs are on. So these main green LEDs right here, these come from the accumulator. They are considered the main output. Will show like calculations. So if you do +1, it will show +1. The program counter outputs are right here. This is for the multiplexer, and this is the address. So if I go ahead and advance this code, this is the Feinberg code. We will see we are on program line 1. Now we are on program line 2. Once we hit program line 3, we should see, once we go again, we'll see, there we go, we did 0 plus 1. Now if I do it one more time, it reset to 0, so the go-to command is working. And then we go again, plus 1, that's 2. And if I keep going, I'll actually set this to the astable clock pulse. We can see 3, and then 4. Then if I go a bit faster, 5, 6, and so on. So I've switched this switch up here, which will switch between the Feinberg code and my code. So mine will act as a vending machine. If we go ahead and turn on the astable clock, we will see this will go from 15 to 10 to 5 to 0 and back to 15. So it should count up 10, and then it will turn down to 5 as we remove 5 cents needed. So 15, and then it goes down to 10, and then it'll go down in a second, bit more, to 5, and then 0. Once it hits 0, it'll go through a couple more lines and then reset to 15, 10, 5, and 0.